Okay. So, in the previous class we discussed about a stress tensor, and then we have derived conservation of mass and the linear momentum balance, and then from general incompressible Navier-Stokes equation we discussed some limiting cases. Before we attempt any problem, as you can see the equations are highly nonlinear. So, we will not be able to solve immediately, even numerically it will pose a lot of challenges. For that matter, the existence and uniqueness of these Navier-Stokes equations mathematically is still an open problem. Okay. So, in order to solve any problem, we have to consider a geometry, right. Once you consider a geometry, what is the immediate question which comes to our mind is, on the boundaries of those geometries, what is the corresponding physical phenomena that one has to consider. So, that is the biggest question to be asked. Okay. So, today we are going to discuss in brief the reduced Navier-Stokes equations for a simple configuration, and then for those configuration how the corresponding boundary phenomena will be implemented. Okay. So, let us recall quickly the governing equations. So, this is a unsteady viscous incompressible. So, most of the times we start with incompressible. Okay. So, this is the local rate, this is the convective rate as we have discussed, and this is the pressure, viscous forces and body forces, and this is the corresponding equation of continuity. If the flow is steady, that means there are no variations with respect to time, we neglect this. So, we get the corresponding simplified equation. Okay. So, now let us restrict the flow to 2 dimensions, that means the velocity vector is u comma v. Okay. So, where it is a function of x and y in 2 dimensions, and also the pressure is function of x and y in 2 dimensions. Then what we are trying to do is, we are trying to write down the Navier-Stokes equation in component form. So, this steady case we are writing. So, what we have to expand this. So, u bar dot grad u we have to expand. So, this is nothing but on again u comma v. Okay. So, this will be okay. So, one component we will be getting from u. So, the first component I am writing. Okay. So, the first component will be, so this is a dot product. So, take u first, this is gradient operating. So, the best way is without u, if you do it, you can get it without any mistake. So, first you take the dot product of these two. So, that will be this operating on u comma v. So, this will give you u dou u by dou x, v dou u by dou y. So, that is the first component, and second component okay. So, once we do this, that is what we have written, first component and corresponding to the pressure gradient you get this, and this is a simple Laplacian. So, very straightforward. Okay. And this is the corresponding equation of continuity. So, this is the simplest. So, if you want to decompose in cylindrical or 2D plane polar coordinates or spherical, so you have to know the corresponding gradient and Laplacian in terms of those coordinate systems. And not only that, so here in Cartesian, when we have taken u dot grad u and also Laplacian, straightforward we have pulled out the corresponding components, because the corresponding unit vectors are constants. So, when you operate on Laplacian, so they are 0, they are treated as constants. Okay. But when you use polar coordinates or cylindrical spherical, one has to be very careful when you are operating Laplacian, because the corresponding unit vectors which are say in cylindrical E r, E theta, E z. So, they are functions of the corresponding r theta phi. So, therefore, when you operate So, you have to consider the corresponding variations. Okay. So, this is very important. So, to start with we have considered only Cartesian 2D. So, in component form we have written. Now, let us see further simplification. Okay. Suppose the flow is unidirectional, that means at this stage when we say unidirectional, we are not assuming that u is function of x alone or y alone, etcetera, etcetera. When we say unidirectional, component along only one direction, it could be 0 comma v, no problem. Okay. So, here unidirectional means along x direction we have considered, that is why it is u comma 0. Then consider your equation of continuity. So, then this indicates that since v is 0, dou u x is 0, therefore, u is function of y. So, that is immediate information we are getting. Okay. Then write down the corresponding momentum equations. Dou u dou x is 0, therefore, this is gone, v is 0, therefore, this is gone. Similarly, here since v is 0, this is gone. Okay. And dou u dou x is 0, therefore, this is 0, because dou u dou x is throughout the domain, therefore, the higher order derivative is also 0 and v is 0. If you assume unidirectional, the corresponding information u is function of y, that is also used, then the reduced momentum equations. So, this one can very easily reduce it. Then another additional information that you are getting from the y momentum is p is function of x alone. Okay. So, these two can be combined to infer an additional information. What is that? If you see, I have changed from partial to total derivatives. The reason is straightforward. U is function of y alone. Therefore, the partial derivatives we have switched over to total derivative. P is function of x alone. The same is the case. So, therefore, this becomes a total derivative, and since it is this is also I have written like this. And if you pay attention, this is function of x, this is a function of y, and you just equate them. Okay. So, if you take it the other side, dp dx equals to mu, and this is function of x, this is function of y, both are equal, that means each of them has to be constant. Why? Because this is not on any boundary, this is invariably throughout the domain. Okay. So, that is the first simplification we get it. So, in some sense the pressure gradient is constant if you take it up this one, otherwise the corresponding second order derivatives of velocity constant. Okay. Fine. So, this is one immediate simplification, right. Now, we move on to boundary conditions. So, this is very important. Suppose even in the simplest case you want to solve a problem. So, for example, you have second order velocity equals to constant. So, it is an ODE, you can get the corresponding solution which involves two arbitrary constants. Now, how do you determine these constants? What I am trying to say is, since we have this admits a solution, you can say mu times u of y will be some a y, okay, plus b, du by is constant. So, that is what you get, right. So, we need two arbitrary constants. Okay. So, how do we eliminate? So, that is the question. So, in order to eliminate these constants, what we have to consider a geometry. So, since we are in Cartesian unidirectional, perfect, but you need some geometry, you have to introduce a geometry. So, let us say you are introducing a flow over a plane. Okay. So, then the question comes, what are the corresponding boundary conditions on this plane, so that we use those and eliminate these arbitrary constants. So, that is the concern. So, now we introduce in a generic sense what are the boundary conditions. So, to start with, let us say you have a boundary which is stationary, then when you have a fluid molecules adhering to the surface, you can have two thoughts. What are the two thoughts? One is the flow is very viscous, and other thought is the flow is inviscid. Okay. So, correspondingly do you expect some change or you think the phenomena remains the same. Okay. So, that is a question. So, maybe some people based on the intuition they would postulate, oh no, compared to viscous and inviscid there should be a change. Somebody may say immediately we can't see any change. We expect if the surface is impermeable, all that we can expect is nothing penetrates. So, therefore, we expect the normal velocity is 0, that is immediate based on general physics one can conclude. Okay. So, let us have a look at it. Okay. What are these corresponding boundary conditions? So, you consider an interface, okay. It is fixed, that means it is not moving, and this is a normal and this is the corresponding reaction. So, the fluid and the surface with which contact is maintained must have the same velocity normal to the surface. Okay. So, what does it mean? Fluid and the surface with which contact is maintained must have the same velocity normal to the surface. So, what is the assumption here? As I already indicated, the assumption here is it is impermeable, nothing can pass through. Okay. So, therefore, normal there is no flux. So, therefore, normal velocity is 0. So, if n bar is outward normal, so then q dot n is 0. In other sense, fluid velocity is everywhere tangential to the fixed surface. That means, the velocity is only tangential to the surface, normal there is nothing penetrating, but on the surface it is moving. Okay. So, that is immediate. This is typically known as kinematical boundary condition. Okay. Now, let us consider the case where the surface is moving with a velocity u, surface is moving with velocity u and fluid velocity is q. Okay. So, then again we expect since nothing is penetrating, the fluid adhering to the surface should move along with the velocity of the surface. So, correspondingly, if you consider the relative velocity, the normal component must be 0. So, that is what we are doing. Okay. So, this is the relative velocity, this is the velocity of the surface and this is velocity of the fluid. So, the relative velocities normal component is 0 because nothing is penetrating. So, previous case is when the surface is fixed and this case is when the surface is moving and this is the corresponding kinematical boundary condition. Okay. Now, something called free surface. What do you mean by free surface? So, some surface is moving with space and time, it is not like a flat or it is very regular. So, it is moving. So, it is depending on both position and time. So, that is called a free surface, okay, like a wave. So, on a sea top etcetera. So, in free surface can be represented by a functional relation of position and time and that is equal. Example, you can take y equals to some function of x comma t in 2 dimensions. Now, the outward down normal is this, very straightforward. Hence, q dot n is u dot n, so that implies because we assume the corresponding the magnitude of the gradient is non-zero. So, this is very straightforward calculation. Okay. Now, one assumption what we use is if you have a free surface, whatever particles sitting on that they will not leave. Okay. This is the kinematic assumption. What do you mean by that? You can see if you drop some particle, so they will be oscillating like that. Okay. So, they are not escaping unless you give some large external forces, right. So, with that assumption the material derivative vanishes. Okay. So, that means whatever the materials on the free surface they are intact, they are not leaving the surface. So, under that so the material particle always remain on the surface, therefore, the material derivative is 0. This brings in some relation, this is we have expanded, this is the velocity with which the surface is convecting. Okay. And hence, we can this we had already because n bar is nothing but this, but from here we are getting. So, we can now we want this normalized by magnitude of the grad f, therefore, with simple algebra we can get. Okay. at a free surface u dot n is this, okay, and hence q dot n is this. We have used this relation in this, nothing great about this. Okay. So, that means, if you have a free surface, then you compute the normal velocity, then if you balance the corresponding kinematic condition, what we get is the fluid velocity normal component q dot n must be related to the convection, how it the corresponding free surface getting convected. So, that is related in this fashion. Okay. So, you can reduce it if f is stationary, then this is 0, therefore, you get usual kinematic condition for stationary. So, this is the first thing. So, quick inference, the first question you recall, what was the first question that we have asked? Whether there will be a difference when you have a viscous and inviscid. Okay, that is the first question. So far what we discussed is, we have normal is 0, because there is nothing is penetrating, assuming it is an impermeable surface. Okay. Suppose you have some permeability of the surface, then what you expect is, whatever normal flux entering, the same amount will come through, okay, as long as there is no surface reactions happening on the surface. Nobody is sitting on the surface who is eating or producing more. So, this is typical assumption. All that we get is, the normal velocity is continuous, if it is there is a porous. Okay. But since we are assuming it is not permeable, so we got q dot n is 0, right. Now, if you consider viscous case, do we have this and that is all or anything else, that is the question. Okay. So, at this stage what we are making a remark, the kinematic condition that the normal velocity of the fluid in contact with the moving boundary is equal to the normal velocity of the boundary, this holds for fluids whether viscous or not. Then what is so special about viscous fluid? So, that is the question, right. You imagine you have a plane, then you have a viscous flow, then what you expect due to the viscous effects, the layers which are close to the plane. So, they are experiencing more roughness, more friction due to the surface roughness. Then the layers far away from the surface, you expect, at least based on intuition, the impact of the boundary should not be seen far away, right. So, that means there is something more happening near in case of viscous flow. Okay. So, what is that more? So, that is what we are moving. When a viscous fluid is in contact with a solid, the tangential velocity of the fluid and the surface agree. This is adherence condition or no slip condition. Okay. The tangential velocity is same. This is the called typically no slip condition. Now, as I already indicated, the no slip condition prevails more in a layer, thin layer above a boundary, because you do not expect far away from the boundary, viscous effects are more prominent. So, therefore, so the no slip condition, whatever we are saying, tangential velocity equal to tangential velocity of the surface. So, this is more prevalent within a thin layer. Moreover, so there is another paradox here. You take the viscous limit going to 0 and then take the inviscid case. So, whether these two agree. So, that is that is a paradox. So, unfortunately, so these two solutions do not agree. So, this we can discuss little more later on, but at this stage this remark is sufficient. Viscous flow case mu goes to 0 is not a valid approximation to inviscid flow. Mu 0 is perfectly inviscid flow, but you take a viscous flow solution, mu goes to 0, will not agree with this. Okay. And this already I have indicated, it is valid in a thin boundary layer. Okay. Then typically when we talk about exterior flows, right. So, you are talking about a flow past an object, then what are the boundary conditions you expect? On the boundary of that object you expect boundary conditions. If it is a viscous flow, immediately what are the boundary conditions we go for? We go for the kinematic condition and the no slip condition. Okay. One important point here is, many times many of the literature they indicate that u bar equals to 0 is no slip. Okay. So, when I say this is very much I would like to make a point of this. So, here we are writing say q bar equals to 0 on say some boundary, and they comment that this is a no slip condition. Okay. So, this is slightly misuse of notation, because when you say q bar is 0, what we mean is the normal is 0, tangential is 0. So, these are, if you are in 3 dimensions, we have 3 scalar conditions. This is one scalar condition and 2 tangential components. So, 2 scalar conditions, this one. Okay. But strictly speaking, this is called no slip, whereas this is kinematic. Okay. But most of the times people misuse, they mention in loose sense no slip means q is 0. Okay. So, but strictly if you want to categorize, normal is called a kinematic condition, tangential is called no slip condition. Okay. So, now let us come back to our exterior flow case. So, you have a flow past an object, apart from the kinematic and then the dynamic condition or the slip no slip condition, what happens at far field? Like, so you have a flow and you have thrown an object, do you expect the disturbance will go to a large extent? It is impossible. Whatever disturbance with whatever intensity you create, at some stage it dies away, right. So, we expect a far field condition, right, either the disturbance is vanishing or something is provided at far field. So, that is called a far field condition. If some ambient conditions are given, the velocity agrees with some given ambient flow. So, that is a far field condition. Okay. Now, with this it is done, but it is exterior case. Suppose you are talking about interior case, like let us say flow inside a ball or some cavity completely closed, right. Then if you solve, you may get terms which are singular at a particular point. Okay. So, like you consider terms of order 1 over r in a sphere, then what happens at r equals 0, it blows up. So, now it is up to the physics of the problem, are we allowing some singularities inside or we are ruling out singularities. So, correspondingly we have to take for interior flows the boundedness condition at r goes to 0. So, this is the difference between exterior and interior. Okay. So, you have a boundary condition, then you have a far field condition, then you have a boundedness condition for interior flows, that is a complete package. Okay. Now, let us revisit the corresponding no slip condition that we have discussed. So, we said no slip means the tangential velocity is equals to the tangential component of the velocities of the surface. So, if the surface is stationary, then q dot t is 0, right, that is what I have written just now. Now, is this enough, or there are cases where this has to be reconsidered, that is the question. Okay. And what are these cases typically? Okay. So, you consider varying material surfaces, right. So, then when you vary the material surfaces, what could happen? So, simplest case is let us say you have taken a glass, then you have taken wood, then you have taken some metal. So, then do you expect in all these 3 the corresponding no slip condition prevails, or we have to think of some correction. So, that is the question. Okay. So, in this context, let us visualize, you might have seen many times there will be some leaves where you have some roughness. On these leaves, what you would have seen, if some drops of water if you put, so they will not be very stationary. So, due to the small roughness on the leaves, typically lotus leaves, you will see the drops are little, they are not completely taken rest and then they are like no slip, but they are slightly you can see elevated at the corners. That means there is something more happening when the surface is slightly rough. So, that is the onset of considering slip. Okay. So, what is this slip condition? Okay. So, the corresponding tangential velocity is no longer the way we have considered tangential velocity, relative velocity is 0, it is not that. Okay. This is kinematic is fine, tangential we are revisiting. Okay. So, what we are revisiting, the tangential component is proportional to the sharing of the corresponding tangential component, and the proportionality constant is called lambda, which is the slip condition. Okay. And this there are experiments to validate this particular condition, and the experiments revealed that this particular slip condition is more relevant in microfluidic environment, not at a global scale. Why? What is the general logic? The general logic is you are considering macro scale. So, you have a surface here and you are considering flow in a large container. So, the corresponding dimensionality do not bother the micro level surface roughness. Okay. So, they do not bother, but if you are in a micro level, the surface roughness also matters. Okay. So, you will see for example, if in Cartesian how the corresponding slip can be written. So, q dot t lambda times this is a normal and a q dot t. Suppose our surface is y equal to constant. Okay. Then what will be the normal? Normal will be E1, right. So, what will be the corresponding velocities if you u and then v, suppose you decompose, then tangential velocity will be corresponding u, this equals to lambda times normal derivative will be along y. So, therefore, dou by dou y of u. So, this is slip condition for 2D. If you have 3D, correspondingly you will. And now, the immediate question is what is this lambda we are talking about? What is this slip coefficient? Are there any physical insights to control this? These are the questions. Yes, there are physical insights to control this. What are they? So, this really characterizes the surface roughness. Okay. So, how you can visualize? We expect no slip, that means particles adhering to this, they are at rest when the surface is rest. If the surface is moving, the particles are also moving with that, therefore, it is 0 here. But in partial slip where you have lambda is finite, then due to the surface roughness the velocity is not 0 on this, is somewhere slightly interior of the surface, and this is called the slip length. Okay. And this is perfect slip. Well, this is again bit of a hypothetical. Perfect slip means fluid particles are continuously slipping on the surface. Okay. And this lambda depends on the material, that is what I meant. If you take a glass surface, you take wood, you take some metal surface. So, the surface undulations at micro level, it is not crisp boundary like that. So, the boundary is you have some undulations. So, this causes slip. Okay. So, that is so you can have a better visualization with this. So, this is the droplet that I mentioned on leaves. You see it is almost taken rest, that means the particles are completely taken the velocity of the surface, the drop is very much rested. This is nothing but no slip, lambda equal to 0 case. Okay. If you see here slightly at the edges it is elevated, slightly the edges are elevated. Okay. So, here the surface roughness is slightly elevated. So, the surface roughness is causing the velocity is not 0 immediately, it is somewhere interior. Okay. Then you see it is almost dancing kind of, it is floating. So, it is a lambda goes to infinity, and this is lambda finite, okay, and this is lambda 0. So, correspondingly the surfaces are characterized as hydrophilic, hydrophobic and super hydrophobic. Okay. So, you can see lot of examples to indicating this. So, these are the various types of boundary conditions, and depending on geometry, of course, we have to resolve the corresponding normals and tangential vectors, and depending on the coordinate system, one has to adopt and then solve various problems. Okay. So, with this, for a simple configuration reduced Navier-Stokes, you will be ready to solve problems. In the coming lecture, we discuss more about some specific configurations and how to get the solutions. Thank you.